When talking electrochemistry and we talk about voltaic cells, the main thing you want to remember is we're talking about a spontaneous redox reaction. We are talking about the types of reactions that we see in single replacement reactions where we have one metal that has slightly more reactivity than another metal, and we see that spontaneous exchange of electrons so that we produce this buildup, this precipitation of one solid where the original solid goes into solution. Now, in a voltaic cell, what we want to do is we want to capture that flow of electrons through an external device so that when these electrons go from one substance to the other, we see and we can capture that electron and turn those electrons into some form of work and look at and produce volts. We produce energy that can be used. Now, the setup is known as a voltaic cell. It's also known as a galvanic cell. When we talk about cells, usually you're dealing with either galvanic voltaic or electrolytic. In both, we utilize redox. One generates energy and one releases energy. Voltaic always produces energy. It's always going to produce some form of energy, generate energy that we can use elsewhere. The other thing you want to remember is where redox occurs. So what's in essence happening when we talk about a voltaic or even an electrolytic cell, what we've done is we have separated the redox reaction. For lack of a better phrase, we've separated them by space and time. The second thing is no matter what cell we look at, oxidation will always occur at the anode and reduction will always occur at the cathode. Now, you can remember this a variety of ways. You can remember an ox and a red cat, or you can remember that the consonants go together and the vowels go together. It doesn't really matter how you remember, you just have to know that no matter what. Now, here's the second thing that you have to remember about any voltaic cell is that we have to have a way to keep the charges of electrons flowing. Since this is a spontaneous exchange, okay, from the anode to the cathode, okay, the anode has oxidation, so we're releasing electrons. The cathode is absorbing the electrons. We have reduction occurring there, so we get the solid. The problem is that as I change the charge within the beakers, there has to be a way to maintain the flow of electrons. And that really is the role of the salt bridge. Without the salt bridge, the spontaneous reaction, the spontaneous exchange of electrons would not occur. And what it boils down to is in this spontaneous reaction, in order for it to continue, you have to keep all the charges balanced. That means as I add protons, because of oxidation at the anode, that means you're adding some positive charge here. There has to be a way to add negative charge, and that's the role of the salt bridge. Conversely, if I'm taking away positive charges, you have to be able to replace that positive charge that's being taken away. Hence, cations go to the cathode, anions go to the anode, and we can maintain a flow of electrons because as that exchange occurs of electrons and we change the ions, we have a replacement, and that is the purpose of the salt bridge. Now, the other thing to keep in mind is how the mass changes. This means if I have reduction and oxidation occurring, since I have an electrode in there composed of the metal, literally the mass of the metal changes. So again, if I have reduction occurring and I have copper reducing, that means I go from copper ions to copper solid, and this is where we get the phrase fat cat, because that means the mass over here is increasing. Now, that means we have an equivalent mass reduction on the anode side. So the anode is actually losing mass because that solid is being oxidized, so it's going into solution. Now notice I didn't say it was equal mass, I said it was equivalent mass because it's still based on the chemistry, it's based on the stoic. So if copper weighs a lot more than zinc, then the mass is going to be much greater than the loss of mass over here, but it's still stoichiometrically related because it's ultimately a stoic problem. It's ultimately, when we talk redox, you're still looking at that kind of change. Now, since the reaction is spontaneous, not every reaction is equally spontaneous. In other words, not every reaction will have an equal difference in the anode and the cathode in terms of their identities. In other words, not any and all metals are equal in terms of producing a battery, because ultimately when we talk about a voltaic cell, that's what we're talking about. We're talking about something that generates energy. So since this is based on a potential, what we deal with is something known as electromotive force, and this is our cell potential. Whenever we are designing a battery, designing a voltaic cell, ultimately what you want to do is you want to have as great a difference in your cell potentials as possible. Now, this difference is what helps to make it more or less spontaneous. Ultimately, when we deal with the definition of cell potential, we measure it in volts. We have a relationship between volts, coulombs, and joules. So our basic definition is 1 volt is 1 joule per coulomb. And it is based on what are known as standard reduction potentials. Now, standard reduction potentials, as you can see, go from positive to negative, and it's written as a reduction reaction. What's interesting is notice that the metals here are written as reduction reactions, and we know that metals tend to oxidize more readily. This goes back to a lot of the stuff that we talked about previously when we talk about the periodic properties, and you're looking at electronegativities, and you're looking at ionization energies, and you're looking at all of those things that play a role in how different elements behave in terms of their reactivity. So when you look at this, you can see that fluorine is the most positive in terms of the reduction half reaction, and lithium is the most negative. Well, that kind of makes sense because we know lithium's the most active metal, meaning it most readily oxidizes. So the thing to keep in mind is if I reverse these reactions, I'm looking at an oxidation reaction, and notice that my volts will become positive. So you're looking at a lot of things. When we talk about E-cell, though, one of the things that we're dealing with is we're dealing with the reduction potential at the cathode minus the reduction potential at the anode. The significance of this, and the reason I point this out that, again, it's a negative, is because what you plug in is you're plugging in the actual reduction. So if you look back at this list, and I erased a few things so that we could look at this, if we look back at this list and we want to find something that would be a good battery, you can look on here and you can see that nickel is right here, and we can go up here and we can see silver is right here. So there is a difference in their reduction potentials. The more positive, more likely to be reduced. The more negative, the more likely to be oxidized. And so what we see is we have a difference. As long as we have a difference, I can generate an electromotive force because I can have an E-cell. I have a difference in the reduction potentials, therefore I have a spontaneous reaction. Now, the example from the book uses hydrogen and zinc. So what you can notice is we see that zinc, okay, so the oxidation has a reduction value of 0.76. Okay, well again, this is actually an oxidation reaction, so if I reverse that, okay, I end up with this reduction value of 0.76. When we look at the reduction of hydrogen, it's 0.34. Again, since my E-cell equals the cathode minus the anode, the overall E-cell value is going to be 0.34 minus a negative 0.76, and you end up with a 1.10 volts. In other words, this is a spontaneous reaction, and it will generate charge. So ultimately, when we look at this, what we really care about and what we're actually looking at are the effects of oxidizers and reducers. Okay, you don't have to know oxidizer versus reducer, but what you do have to know is if we are talking about something that undergoes oxidation more readily, it is more active. So this goes back to the activity series that we talked about way back last semester when we looked at the reaction types. And an activity series is, in essence, what we looked at on our reduction table here. When we go down here, these elements readily oxidize. That means on our chart here that a lot of our differences, so most difficult to reduce is lithium, okay, that makes it more likely to donate electrons, that means it's more likely to cause something to undergo reduction. And that's all when we talk oxidizing, reducing agents, oxidizers, reducers. You don't necessarily have to know the term so much as you do have to know that elements that have the most positive reduction potentials will undergo reduction, and the elements with the most negative reduction potentials will undergo oxidation. And that's really the point. That's really what you want to know. The main reason for this is if we're creating a battery, if we're creating a voltaic cell, we want the greatest difference between, we want a huge reduction potential difference. We want the greatest difference between them. So if we look at copper and zinc, we get a difference of the 1.1. That's a big difference. That's going to be a nice spontaneous voltaic cell. So we're going to generate a fair amount of volts. Now this ties into free energy because ultimately what's trying to go on with our voltaic cell is it's trying to attain equilibrium. So this spontaneous exchange of electrons will eventually stop because eventually there's no more electrons to donate, there's no more copper to remove, and literally an equilibrium is established. So the importance of this ties into what we talk about with delta G. This is a spontaneous reaction, therefore my delta G has to be greater than 0. So ultimately delta G for spontaneous has to be greater than 0. Well, as a voltaic cell is occurring and producing volts, delta G is always greater than 0. But at a certain point, my E is going to equal 0. And if my volts equal 0, that means my delta G is 0. And equilibrium has been reached. There's no more reaction occurring. Now, notice that our equation for delta G depends on a couple of new ideas. N, number of moles, no big deal. F is Faraday's. Faraday's has to do with the relationship between coulombs and moles, and this is ultimately has to do with the exchange of electrons. Okay, now, since standard conditions, quick reminder about standard conditions. Standard conditions are 25 degrees Celsius and 1 atmosphere. So it's not STP, it's standard conditions. The reason this is important is sometimes you're going to have to deal with a cell that is at non-standard conditions. Now, technically you have this thing called the Nernst equation, which lets you calculate what's going on at non-standard conditions. Guess what? You don't have to know this for the AP exam, but what you do have to know is you do have to recognize, looky there, you need to recognize that Q is in this equation. And the importance of this is that Q, as we all well know, we can use Q in terms of equilibrium. And so Q tells us how far from equilibrium we are. Well, guess what? When you are trying to determine the best battery and get the best E, you are literally dealing with a situation of creating a situation that is far from equilibrium. The distance from equilibrium is what determines my value of E. So we've been playing with this all along. The significance of this when we look at Q then means that our concentrations can play a role. Whoops, I can't really put a square on concentrations. Ultimately, if I change conditions, so I change the reaction and I take it away from equilibrium, if I change concentrations, I change Q because Q will be greater than 0. Again, remember log of 1 is 0. So if I change the concentrations, meaning I can have the same substance at different concentrations. Well, this ties in directly with what we've talked about with Le Chatelier's. Whether, as the book discusses, you're dealing with the same substance at different concentrations, or you are simply looking at our oxidation reduction reaction and dealing with it that way, if I change the concentration of this, if I increase the concentration of my zinc, well, I'm going to kind of slow the reaction down because it's going to shift it this way. If I change the amount of this, I meant to circle this 2 plus, I'm actually going to shift my reaction a little to the right and speed it up. So I'm going to have an impact upon the rate of the reaction. I'm going to have an impact upon the number of volts produced simply by changing the concentrations, whether it's the same substance or not. Again, because we're dealing with Q, and we know that Q has that relationship to K, the mass quotient, depending on where Q is, greater than K or less than K, I have an impact upon what's going to happen with my delta G. I have an impact upon the spontaneity of the reaction. So as Q approaches K, that means my delta G gets smaller and smaller because I'm closer and closer to equilibrium.